Hi guys, welcome to our first Q&A brought to you by the ChemEng Student. Now in this series we're going to take questions from our students through both our website and our social media platforms. So this particular Q&A, our first one, is going to be on Reactor Design. So my name is Callum Russell, I am a PhD student. I also hold a Master's and Honours degree in Chemical Engineering, and you can find more information about myself on our website. So as we said, in this series we're going to take a look at several different questions that have been submitted by our students, and in this case we have a few questions submitted in terms of the reactor design. Now this can be across all levels. It can be from first year to master's degree, so please feel free to get in contact and visit us here at thechemengstudent.com. I'll put a link in the description to our website. So the first question was submitted by Declan12, and he asks, can you derive an expression for the reactant exit concentration for a CSTR of a second order reaction? So we have a couple of key terms here that we need to consider. We have an exit concentration relationship, we have a CSTR, and we have a second order reaction. So there's three main components of this problem, and this is just a very generic CSTR. So the way that I would attempt this problem is as follows. So I'm going to write the basic and general balance over a CSTR. So we have the input is equal to the output, plus or minus the generation, plus or minus the accumulation. Now what we can then do here is say that our input, we have a flow because we have a CSTR. So we have F naught, that's our flow, Ca naught is our initial concentration, F is our outlet flow, Ca is our final concentration. We have our rate of reaction minus Ra multiplied by the volume plus the volume multiplied by the partial differential of the concentration over time. So this would be the accumulation term. Now there are a couple of assumptions that we can make in order to simplify this problem. The first one being that we can neglect the accumulation term, because what we assume here is we have steady state conditions. So if we have steady state, that means whatever comes into the system must leave the system. So we have no accumulation taking place. So if that being the case, then what we could then do as another simplification is say that F naught is equal to F. Because if the system is steady state, then the feed of the input must be equal to the feed of the output. So what we can then do is make F naught and F equal to each other, and then divide both sides by F. So if we make this F, then when we divide every term here by F, we see that that would cancel with that would cancel with that, and we're left with this expression here. So we have Ca naught is equal to Ca plus or minus the reaction rate multiplied by the volume and divided by F. And then we can rearrange again so that we get it for the output concentration, so our final concentration. Because remember, the question wants the conversion for the exit concentration. So this would be our Ca. Now, we still have to take into consideration the order of the reaction. So now we're going to turn our attention to the minus Ra term. So we know from general reactor design that the order of the reaction for second order is the reaction rate constant K multiplied by Ca to the power 2. So that's the concentration of A to the power 2. And that denotes a second order reaction. So what we can then do is substitute in this kCa squared into this equation, and we can see what happens here. So now we can see that we have a Ca here, and we also have Ca squared here. So what we can then do is bring this across to the other side, and we can then factorise and take out, we could bring the Ca naught across first, And then what we would be left with is a fancy quadratic equation. Because what we have here is Ca squared Ca and then an independent variable. So this is the same as a quadratic equation, the x squared, the x and the number by itself. So in order to find this, we can apply the quadratic formula. So we denote our values of a, b and c. So a is the kV over f, b is 1 because we'd have a 1 here, and c is the whole minus Ca naught. So if we input this data into the quadratic formula, and that is what we would get. We would get our Ca is equal to minus 1 plus or minus the square root of minus 1 squared minus 4 multiplied by kV over f multiplied by minus Ca naught over 2 kV over f. And that would be the equation for the exit concentration as a function of the initial concentration, the reaction rate constant, the volume, and the flow rate. So that is perfectly acceptable to leave that as your answer, because you would therefore need to know the values of K, V, F, and Ca naught in order to be able to actually solve this. So that is your general equation. So a very good question there from Declan 12, one that was hopefully straightforward for you guys. So we'll then take a look at question 2, and this was submitted by Heather. And she asks, can you solve this equation please? We have a gaseous reaction, A goes to B, and it's conducted at the temperature of 555 degrees Kelvin at a pressure of 300 kilonewtons per meter squared, and we have a tubular flow reactor. So again, that's key here, we have a tubular flow reactor. Feed contains 30% A on a molar basis, and the balance is the inert material. We have a feed rate of 0.0063 kilomoles per second, so that's important. And we know that the rate equation here is given by minus Ra is equal to 0.0033 Ca. So that is our K value here, because we have a first order reaction. So this would be a first order, so minus Ra is equal to K Ca, that's our first order. So we know the value of K here. The value of K is 0.0033. Now we want to say for a 95% conversion, we need to find the space velocity and then the reactor volume that corresponds to a 95% conversion operating at these conditions. So the first thing that we'll do again is we will write out the general equation. Now again, this time we are working with tubular reactors, but the process should be fairly similar because we have an input and an output. We will assume steady state conditions again, so we can neglect this term. We assume that F naught is equal to F, and what we can also assume here is that Ca naught is equal to Ca. So what this means is that with a tubular reactor, what we can do is we essentially take a chunk of the reactor and we model around this chunk. So this here would be the d, Ca, the dx, and so forth, or even dv. So that's why our final concentration is going to be essentially the change from this concentration. So that's the initial concentration, i.e. we've just said that Ca naught is equal to Ca, so that's why we've replaced that with Ca. And that means that the outlet must be Ca plus the differential part that we are modelling here, so that would be this part. So this would be Ca, this is our dCa, and the output here would be Ca plus dCa. Now what we can then do from here is we can multiply this out. So we can do our F times Ca and F times dCa. And what we will see here is that these two terms will cancel. So we now have the equation of minus F dCa is equal to minus Ra dV. So now what we can do is integrate this by, if we look here, we can separate these variables. So we can bring this across to that side and then bring the minus F across to that side, because minus Ra is a function of the concentration Ca. So that's why we have dCA over minus RA is equal to dV over F. Now our limits again are going to be from the concentration to the Ca naught Ca, from 0 to the final volume. So what we'll then do is we can integrate this fairly straightforward, and we know that we would get V over F, because this is essentially going to be 1 over F. We take F out as a as a constant, so therefore we integrate the value of 1, substitute in V, and that'll give us our V over F. And this is our space velocity. So now what we then have to do is replace our minus RA with our first order equation, which is K1Ca. Now we know that K is a constant when it comes to the reaction rate kinetics. So we can take K out of the integral sign, because this is going to remain constant regardless of the concentrations. So what we end up with is the integral. So here what we would have is the integral of 1 over Ca dCa. So then that would give you the log, and then you would have your limits, the upper minus the lower. So that's why we have V over F is equal to 1 over K1 ln Ca naught over Ca. So now what we can say here is this is for, or we were given it in terms of a conversion. So that means that we have to express this in terms of a conversion. So that's the value of x. Now what we know is that Kca is equal to Kca naught 1 minus x. In other words, we can replace the Ca value with Ca naught 1 minus x. So that would be down here. And that way we introduce the conversion factor into our equation, because that's what we need in order to find our space velocity. So when we substitute in this for Ca and we rearrange and we can cancel the Ca naughts, we can get 1 over 1 minus Xa, and that is the space velocity equation in terms of the conversion instead of in terms of the concentration. So now what we can then do is substitute in our values. So we know that the value of K was 0.0033. We know that our conversion that it asks for was 95%, so we substitute in 0.95, and that will tell us that our space velocity is 1.1 times 10 to the minus 3 seconds to the minus 1. And then finally part B, what we can then say is that we have our equation in terms of, so from here, we then know that F over V is equal to 1.1 times 10 to the minus 3. So then we can work out our volume from here. We just rearrange that, and then what we can do is substitute in all our values, because F is now going to be a function of the operating conditions. So that's where we have our ratio between our operating temperature and our standard temperature of 273, our standard pressure, so our atmospheric pressure divided by our operating pressure, our molar volume multiplied by our number of moles. So when we work this out, we get a V to be 88.18 meters cubed. And that's how you would go about solving using this type of system. So again, another fantastic question there from Heather, one that involves some interpolation in terms of the operating conditions for F, but one that shouldn't cause too many problems. And then finally, question 3 is handed in here by Luke, and this one was probably one of our more in-depth questions, one that was slightly more involved and one that we really enjoyed having to solve this question. So here what we have is a first order reaction, so it's a batch reactor this time, and we have A goes to 2C, and we have a volume of 0.1 meters cubed of 0.4 kilimoles per meter cubed of a solution of A. So now we're starting to get the moles, the volume, all that sort of stuff for our individual components. Now, the density of the solution may be assumed constant during the reaction. So that's quite important, because that's one of the assumptions that we can make in order to simplify our system. So again, that really helps us in terms of the maths. Now we have the heat of the reaction, which is minus 200 megajoules per kilomole, and it gives us the rate of the reaction at 15 degrees Celsius to be 0.00134 Ca, kilomoles per meter cubed second. So again, remember this is a first order reaction because we have A here, we don't have any other component, so this is first order. And then we know that the rate of equation at 30 degrees is now the 0.00141 Ca, because remember the reaction rate constant is highly dependent on the temperature. So that will change significantly as the temperature changes. So you can see here that from 15 to 30 we have a change in the reaction rate constant. Now we need to calculate the time to achieve a 70% conversion if the operation is isothermal set at 20 degrees. And therefore we need to calculate the total heat removal that is required at that time. So now we're bringing in a bit of energy balances as well. So we just need to be very, very careful as to how we approach this. But first of all, what we'll do is we'll work out using linear interpolation for the value of Ra minus Ra at 20 degrees, because we have the K values for 15 degrees and 30 degrees respectively. So what we can then do is do linear interpolation. Now we go into the details on how to do linear interpolation in our online courses, so I'll be sure to put a link in the description to our Reactor Design course and also our Mass and Energy Balance course that looks at this in slightly more detail. But essentially what we have is the values, so from 15, the K value at 15 degrees minus the K value at 30 degrees divided by the change in the temperature multiplied by the change between the value that we want, so that's 20, minus the lower value, which is 15 degrees, plus the value at 30 degrees, or K value at 30 degrees. So we can see that the K at 20 degrees Celsius will be 0.001386. So now we have the reaction rate constant at 20 degrees Celsius. Now we know that the time will be equal to the initial concentration Ca0 multiplied by the conversion divided by the reaction rate. So we can replace minus Ra with our rate constant multiplied by our concentration of A. That's the final concentration of A. And then what we can do is then create a differential equation, because this will be as a function of time, because remember the concentration will change as time changes. Because if you can imagine we have a time here and say concentration, then if we have say Ca0, then we could see that as time changes, then the concentration of the reactant will begin to decrease and decrease until it becomes 0. So we can see that the temperature is going to change, the time will change as the concentration changes, and vice versa. So what we'll do is we know that because this is dt, when we integrate this, we will get the value of t. It's because we integrate with the value of 1, substitute in t and 0, we get t. Then what we can do is we can take out k as a constant again from the integral. That's what we've done in the previous question, because that's going to be constant. And then what we can do is we have our 1 over Ca dCa, and what we have done is we have inverted the limits here, and that's cancelled out this negative sign. So by inverting the limits we can cancel out this negative. So then all we need to do is integrate this and substitute in our limits. So we get t equals 1 over k ln of Ca0 over Ca. So then if you can remember from the substitution of our Ca is equal to Ca0 1 minus x, we could pop that in here, and then we substitute in our value of conversion of x to be 0.7, and that would tell us that the time it would take to reach a conversion of 70% would be 868 seconds. So that is how you would go about solving for the reaction time for a given desired conversion. So again, we could test this equation for different conversions and see what one is the most appropriate. Now part B is for the amount of heat that has been required to be removed. So we know that the amount reacted, because we started with 0.4 and then we went down to 0.12. So we know that the amount reacted was 0.28 kmols per meter cubed. Now we can perform a moles concentration and volume calculation, and that would tell us that the amount of moles reacted in this system, because this is the concentration, kilomole per meter cubed, we multiply that by the volume, and that'll tell us that our moles of the system is 0.028 kilomoles. Then we were given the heat of the reaction, which was minus 200 megajoules per kilomole. So we multiply that by the number of moles, and that will give us a Q value of minus 5.6 megajoules. And that's how you would go about solving a problem like that. So again, a fantastic problem there by Luke, and one that we really enjoyed solving. So thank you very much for that. So that's the end of our first Q&A. Thank you for your time, and please be sure to submit your questions. You can see on our social media accounts what the next topic will be. I think the next one will be mass and energy balances, but please have a look on our social media accounts, submit your questions, and we hope to see you in another video.